In this session, we are going to study about air wedge, an interferometric technique using which we can find the wavelength of a monochromatic light, the thickness of the spacer, the refractive index of the liquid, and so on. Let's see how an air wedge is created and how we can measure wavelength, refractive index of liquid, diameter of wire, hair, thickness of the spacer using the air wedge technique. Now, to create an air wedge, we need two optically plane glass plates. These two optically plane glass plates are held together at one end, and on the other end a spacer is kept. So a variable size air film is formed between the two optically plane glass plates. The thickness of the film at the point of contact is equal to 0. So if you move along the wedge, the thickness increases, and if you move across the wedge, the thickness is the same. And theta represents the wedge angle. So this is the experimental setup of an air wedge. We have a monochromatic source, which is a sodium lamp. Light from this monochromatic light source is made to fall normally on the wedge shape arrangement. The reflected light will create an interference pattern which is viewed with the help of the microscope. So let's study in detail about the interference pattern created by the air wedge. Light falling normally on the wedge shape arrangement is partially reflected from the bottom surface of the upper glass plate. The thickness of the air film at this point is T and is lying at a distance of x from the fixed end. And the light reflected from the bottom surface of the upper glass plate, the reflection is happening from a denser, rarer interface. The transmitted light is again reflected from the top surface of the bottom glass plate, where the reflection is happening from a rarer interface. According to Stokes' law, we know when the light is reflecting from a rarer, denser interface, the reflected light will suffer a path change or phase change, and no path change or phase change happen. The reflecting boundary is denser, rarer interface. So when you observe the two reflecting interfaces, the first reflection is happening from a denser, rarer interface. That is, light reflected from the bottom surface of the top glass plate, the reflection is happening from a dense, rarer interface, and the light reflected from the top surface of the bottom glass plate, the reflection is happening from a rarer, denser interface. Now we can calculate the path difference between the interfering beams, namely 1 and 2. Now when compared, 2 is traveling mu t down. It undergoes reflection from the top surface of the bottom glass plate, which is accompanied with the path change of lambda by 2. Again it moves mu t up. So the total path difference is mu t plus lambda by 2 plus mu t. On simplifying, we get path difference is equal to 2 mu t plus lambda by 2. Now, if this path difference is equal to n lambda, that is 2 mu t plus lambda by 2, if it is equal to n lambda, then ray 1 and 2 will be interfering with each other in a constructive way. Simplifying, we get 2 mu t is equal to n minus half lambda. Now from this triangle, which is having one side x, one side t, and wedge angle theta, t is equal to x tan theta. So when you express t as x tan theta, the condition for constructive interference condition takes the form 2 mu x tan theta is equal to n minus half lambda. If the path difference, if it is equal to 2n plus 1 lambda by 2, then the ray 1 and 2 will be interfering with each other in a destructive way. If t is replaced by x tan theta, we can write the condition for destructive interference as 2 mu x tan theta plus lambda by 2 equal to 2n plus 1 lambda by 2. Simplifying, we get 2 mu x tan theta is equal to n lambda. So the condition for constructive interference is 2 mu x tan theta is equal to n minus half lambda, and condition for destructive interference is 2 mu x tan theta is equal to n lambda. When we observe the fringe pattern through the traveling microscope, we see straight line fringes which are alternatively dark and bright. In the case of air wedge, the points of same thickness lie on a line, and that too across the wedge. So, light reflected from one point, if it is satisfying dark condition, then the same condition will be satisfied by a set of points which lie on a line. Therefore, wedge-shaped film always forms straight line fringes. Reason: locus of all points having same thickness which cause the fringe is in a line. Now let's determine the bandwidth of the fringe. The bandwidth of fringe width is defined as a distance between two consecutive bright band or two consecutive dark band. Now I'm going to use over here the dark condition. The dark condition is 2 mu x tan theta is equal to n lambda. Now let m and m plus 1 be the two adjacent dark band which lie at a distance of x1 and x2 from the fixed end. Now we can rewrite the dark condition as 2 mu x tan theta is equal to m lambda, corresponding to the mth order, or x1 is equal to m lambda divided by 2 mu tan theta, and corresponding to the next order, that is m plus 1, I can write the dark condition as 2 mu x2 tan theta is equal to m plus 1 lambda, or x2 is equal to m plus 1 lambda divided by 2 mu tan theta. Beta fringe width is equal to x2 minus x1, which is equal to divided by 2 mu tan theta. For air wedge, mu equal to 1, and from the figure tan theta equal to d by L, where d is the diameter of the spacer and L is the length of the wedge. So in the expression for beta, that is beta equal to lambda by 2 mu tan theta, replace mu by 1 and tan theta by d by L, we can rewrite the expression for beta as beta equal to lambda L divided by 2d. Application of air wedge to find the diameter of the wire. So the given wire is placed between two glass plates in order to make a wedge. Light is made to fall on the wedge shape arrangement, and the interference pattern is viewed through the microscope. From the interference pattern, calculate fringe width, determine the wedge length L, and finally calculate the diameter using the equation d equal to lambda L divided by 2 beta. Application of air wedge to find the surface plainness of a given glass specimen. In air wedge experiment, we use two optically plane glass plates. If the glass plates are plane, then we get straight line fringes. If one of the glass plate, if it is not plane, we will not get straight line fringes. Fringe with bend in them indicate elevation or depression. In this way, we can identify the surface plainness of a given workpiece using air wedge technique.